Okay, no, it comes up later. All right, so let's look at some applications to the human body. The circulatory system has two parts. You need to be able to identify them and tell what they do. You have the systemic circuit and the pulmonary circuit. The systemic circuit takes blood to the body, takes and returns blood to the body. The pulmonary, what does pulmonary mean? If you have a pulmonary doctor, what is that doctor? Huh? The lungs, right? So pulmonary circuit takes blood to the lungs, to and from the lungs. And it takes, I'm going to say, used blood. Oh, that sounds a little sketchy. But it takes blood that has been depleted of its oxygen to the lungs, and then there it's replenished, or replenishment. All right. Get that, be able to identify both of those, know what they do. Everybody get that? I'm going to go back up. Bless you. We good, everybody? Yeah? All right. So we'll consider this system to be closed. The circulatory system is not technically closed, but we'll consider it to be closed. That just means that nothing going in and nothing going out. So the flow rate is constant. You know, the flow rate, remember Q is equal to delta V over delta T. We're going to say that that is a constant value. And so if that's true, then the continuity equation applies. The continuity equation, recall, just said that Q1 was equal to Q2, that if I have a fluid flowing in a pipe, then the total amount of that flow rate has to always be the same. And the result of that continuity equation, I'll rewrite it here. It's a terrible bracket. Let me rewrite that. The result is that A1 V1 equals A2 V2. Okay, so also since blood is viscous, the Poiseuille equation applies. So the Poiseuille equation will apply when you have these viscous fluids, so you can account for that eta, for the viscosity of the fluid. And so for a viscous fluid, we talked about this, but you need a continual drop in pressure. Remember, the Poiseuille equation was that pi r to the fourth delta p over 8 eta L. And so what we need when we have the circulatory system is that we always need this continual drop in pressure in order to keep the flow of blood. You'll need to know the order of blood flow. If you've had A and P, you probably know this, or you've had this in some classes. The aorta, after leaving the heart, it goes to the aorta. I'll show you a picture of that in just a second. Gosh, y'all know where it goes next? The arteries, right? To the arterioles. And then finally to the capillaries. Two L's, right? Okay, and then that's sort of where it's taking oxygen to the body and nutrients, and then when it comes back, it'll return to the heart. Coming back to the heart, we go through the venules, to the veins, and then the vena cava. So if you sort of want to draw, parallels between these, you can think of them in this way, that those are sort of the parallels as they go back and forth in the circulatory system. I want you to know the 4 chambers in the heart. You don't have to know the valves in the heart, but I do want you to know the 4 chambers and then be able to identify the aorta and the vena cava. And I want you to know how blood flows in the heart as well. So the heart is divided into 4 chambers. You have the atrium. Is that top or bottom? It's top, right. It's like you think of it like you go in a hotel. Hotels don't really have these anymore, but they used to. They have big atriums. The atrium is like the thing up top. Right? Okay, so the top part is the atrium, and then it's the left and right, but it's like stage left, stage right. Right? Anybody drama folk in here? Stage left, stage right? Okay, so stage left is like where is over here, right? To your right, and stage right. So it's like if you're looking at your heart, you're looking at the left and right. So it gets switched around is my point. So this is our right ventricle, our right atrium. This is our left atrium. And then on the bottom, we have the right and left ventricles. I'll write these words out just a second. So we have the atrium on the top, ventricles on the bottom, and then just recognize that left and right are switched because of the way you're looking at the heart. When you look at it on the paper, it's switched from what you would expect. Easy peasy? You've seen that before, right? Most all of you have seen it, right? Right? Yes? Yes? Seen this sort of thing before? Okay, if you haven't, you will. It's a good time to pick it up now. So, know the general flow that blood takes in the circulatory system. It flows out of the left ventricle through the aorta, goes through the systemic circuit, goes out to the whole body, and returns depleted to the right atrium. Then it's going to go to the right ventricle, through the pulmonary artery, to the lungs, and returns to the left atrium through the pulmonary vein. I have a figure on the next page that sort of shows this in a picture. Okay? Your book describes this in more detail too. All right, there are 4 one-way valves in the heart. I list them here. You don't need to know them, but they're talked about in the book, but I won't test you on them. I just want you to know the basic flow, how blood flows. I might give you a figure like this or something similar, ask you to identify the ventricles and the atria. I might ask you to identify like the vena cava or the aorta or the pulmonary artery or pulmonary vein. Like I would show you the arrows and ask you, okay, which is this? Is this the pulmonary artery or the pulmonary vein? You can tell because the arrow is going away from the heart, right? The vein is coming into the heart. Same with the vena cava, that's where the blood is returning. Know your right atrium, left atrium, your ventricles. Don't worry about the valves, but you probably need to know those anyway for other classes, but not for this one. Okay, good on the heart. Draw cards. It's probably the best way to quiz yourself on these if you don't remember them, but it's good information for you to know. Let's try these clicker questions. Let's do the one on the right here first. We'll come back to that one about the the artery blocked. So just leave this one for now. Go ahead and do this one right here. Oh no, don't worry about that one. Let's go to this one. Sorry, those two are related. So we'll just do the ones on the bottom, and then we'll address those top two. The pulmonary circuit does what? And the one on the bottom left. Bottom left. I'm going to stop at 55, 55. Okay, good. A is right. It takes blood from the heart to the lungs. And when it goes, so it takes that used blood or the depleted blood from the heart out to the lungs. And then in which of these is the rate of blood flow the greatest? It's bottom right. Is the rate of blood flow, Q, that is it greatest in the aorta, capillaries, the venules, or is it same throughout all the systemic circuit? Feel free to ask your neighbor what they put. Encourage you to do so. Okay, let's stop at 50. 50 seconds. Okay, good. So you're sort of stuck between A and D. And it seems like the aorta, right? It's a big old thing. I can stick my pinky in the aorta, right? And so it should have the larger blood flow, correct? But do you know there's only one aorta? But there are, I don't know, thousands of capillaries, not more, tens of thousands, a lot of capillaries. So you have the same blood flow throughout both of those. And even though the aorta is much, much bigger than the capillaries, you have a lot more of the capillaries. You only got one aorta. Stick your pinky in there. But you have a lot of capillaries. So because we're assuming that this is a closed system, that means that Q1 is always constant throughout the circulatory system. So it's going to have the same blood flow at every point in the system. We'll talk about how that comes to be, how the continuity equation is impacted there, or how it comes relevant. Let's talk about these first two questions. I'm not going to ask them of you. I might ask them of you on the quiz, on the test. But there's a new principle that comes up here. This is not in the book, but I could quiz you, I could test you on it. So this is one thing that's not in the book, but it's kind of important. And it's called Bernoullis Principle. Bernoullis Principle not in the book, correct? Y'all recall that? No? Our Bernoullis Principle isn't complicated. I'll sort of write it up here. Bernoullis Principle. It's based on the conservation of energy, which I know we haven't seen yet. We'll see it in the next chapter. But in short, it says this. For a fluid that is flowing, if V goes up, the velocity of that fluid, if it goes up, then the pressure of that fluid will decrease. So the big application of this is on an airplane. And it's the principle behind airplane wings. Airplane wings look like this. They're flat on the bottom. They're curved on the top. And when you have air that comes along, you'll have a stream of air that comes along this airplane wing. And it'll split into two pieces here. One piece will go on the top, and one piece will go on the bottom. Now, because of the way nature works, you can't create a vacuum on either side of these. So if you imagine that you have two particles of air, as they travel along this wing, they have to come back at the same point. All right? So if I have two particles of air here, they're going to travel along this wing and then come back at the same point. So which side, the top or the bottom, will the air travel faster? The top or the bottom? Huh? Did you see the look on my face when it said bottom?
Yeah.
Right, yes. Top. Because they have to come back at the same point after they go over the wing. And this one's traveling a longer distance. So it has a longer distance and a shorter amount of time. It has to travel faster to get over the top of the wing. So which side is it traveling faster, the top or the bottom? Did you say bottom again? Which side is it traveling faster? The top, yes. So because it's a longer distance, same amount of time as the bottom, so it has to travel that faster. So I have high velocity on top and low velocity on the bottom. But Bernoullis Principle says that if V goes up, the pressure goes down. So over here I also have low pressure here and a high pressure here. That means that I'm going to get a net pressure that's up, or a net force that pushes up. That's called a lift. Really sore. Went to the gym. It was like 3 days ago I went to the gym. When I was 20, I could go to the gym and I'd be recovered in like half a day, but now I feel like it takes me about 3 days to recover. Okay, so look, I have a ping pong ball and a cup, and I'm going to put a high velocity stream of air across the top of the cup. What's that going to do to the ping pong ball? It's going to lift it, right? Because when I blow that high velocity stream of air, on top of here, it's going to have what, a high or low pressure? High velocity, low pressure. Velocity goes up, pressure goes down. And then it'll have a high pressure inside of the cup, and that will lift the ball up. You see that? You see? That's kind of cool, huh? All right. Well. Okay, so if I have a high velocity stream of air, let me do this too. This is kind of cool. This is my hair dryer. I'm going to have to do it over here. You have a hair dryer at home? Right. So I can create a high velocity stream of air with this, and it creates a region of low pressure inside the stream of air, and then that's surrounded by a region of high pressure. High velocity, low pressure. So it creates like a column. So it's fairly well protected. Look, I can even sort of bend it off. I can move it around. It moves up a little bit. At some point, the weight of the ball just exceeds the difference in pressure due to the hair dryer. It's not the blowing air, right? It's not like the air is holding it up. It's that it's creating a region of low pressure. And then the pressure on the outside is keeping the ball inside of this column. Okay? That's Bernoullis principle. And it's important here because if I get an area of plaque, what I've done is I've decreased, if I get plaque inside of an artery, I've decreased the area of that section. So let's try this question, the one on the left, and I'll add an additional question. The first is not really due to Bernoullis principle at all. It's just the continuity equation. But what happens to the speed of the blood flowing through this blocked section? Does the speed of the blood increase, decrease, or stay the same? Not really Bernoullis principle here. We're dealing with something else. But let's ask this question. All right, let's stop at 1 minute. 1 minute. Okay, A is the right answer. This is just continuity equation. It goes back to this equation where A1V1 equals A2V2. And we said that if one of these goes up, the other has to go down. So here, our area is decreasing. That means that our speed must increase. So the answer here is A. The product AV is constant. If area goes down, which is what's happening, the area is decreasing. That means that the speed has to increase. It's like putting your finger over the hose. That's what happens in your artery when you get this plaque buildup, is that the blood begins to speed up going through that section. Let's ask another question, and we'll use the same one. What happens to the pressure in that region? To the pressure of the blood flowing through that region, what happens to it? Does it increase? Use the same options. Increase, decrease, or stay the same. Does the pressure flowing through that artery increase, decrease, or stay the same? Okay? All right, what? Y'all are pretty much evenly matched between A and B. What does Bernoullis Principle say? If the velocity goes up, what happens to the pressure? No, say it out loud. Sorry. But ask your neighbor, if the velocity goes up, what happens to the pressure? And so what's going to happen to the pressure right here in this artery? All right, let's stop at 1:15. Most of you have it right, but you're not going to get a joke because I actually gave you the answer, okay? All right, the answer is B, right? And I know that doesn't make sense because you think, oh, if I get buildup in my arteries, that causes my blood pressure to go up, right? But that's not what I'm asking. I'm asking about the localized blood pressure. And right here at this point, because I have a faster flow of blood, I'm going to have a lower pressure. Because I have a high velocity of fluid, I have a low pressure. And so you can have this affect people where they get such a low pressure right here that they'll have what? Do you know what that's called? You just get like arterial collapse. The whole thing, you'll get this pressure pushing from the outside, and you get such a low pressure that this whole thing just collapses in on itself. And of course, that's bad. I mean, that's worse than having plaque in your arteries. Okay, well, let's try this next question. So the next question is asking something different. It's asking, what is the overall blood pressure, like the blood pressure in your body, if a blood vessel becomes partially blocked? And you can think about this in terms of our Poiseuille equation, which is pi r to the fourth delta p over 8 theta L. And so it's asking if the artery becomes blocked, that means that this is going to decrease. What is going to happen to this? What happens when I decrease the radius of my artery? What happens to the overall systemic blood pressure? Okay, good. I'm going to stop at 1:15. 1:15. Okay, good. A is right. And that's sort of what you would think, that if you get this blockage of your artery, then you'll have an increase in blood pressure. But again, This is not a localized blood pressure because locally your blood pressure decreases by a lot. But according to the Poisson equation, I think that governs our flow rate of blood, where Q is constant because it's a closed system. If this R goes down, then this P is going to go up by a lot. Like if our R goes down by a factor of 2, then P is going to go up by a factor of 16. So the pressure is heavily dependent upon the radius of the system. Okay? Remember, 2 different pressures we're talking about. We're talking about a localized pressure that if it gets too low, you can have arterial collapse. And then you have an overall systemic pressure, which is determined by this delta P. What is the difference in pressure between 2 different points of the system? Follow me on that? I would expect to see some questions about that on Tuesday. And again, Bernoullis Principle is not in the book, but I'll ask you some basic questions. If the velocity of a fluid goes up, what happens to the pressure? In which you would say the pressure goes down. And I might ask you some application like this artery question. Okay, good. I like Bernoullis Principle. It's kind of fun. We might talk about it later. It's based on the conservation of energy, which we're going to get to in the next chapter. So we might come back to it. All right. So as blood flows through the systemic circuit, it experiences a continual drop in pressure. And the highest pressure, well, you tell me, where is in the systemic circuit, where is the highest pressure? You don't know? What is, I'm sorry, what? That's right, it's in the aorta, because the aorta is the first place the blood goes after it leaves the heart. And so you're gonna have that highest pressure just as it squirts out of your heart into the aorta. And then it goes through the whole systemic circuit, goes to your toes and your fingers and all that, and it comes back. Where is the lowest pressure going to be? Right, vena cava. Is it really cava? Or did you just make that up? Anybody else know the correct pronunciation? Cava? You feel schooled? Okay, good. All right. Poissy's law also says, let me write Poissy. For the test, you will also have to say Poissy. Yeah, go ahead, try it. Poissy. Yeah, see, Poissy. All right, pi r to the 4th, p over 8, a to l. It says that the pressure, and it's really the pressure differential, right? The delta P, which would be like the difference in pressure in the aorta and the vena cava. That this pressure difference must be higher for flow through longer systems. So delta P, if L goes up, that means that delta P goes up. If L increases, delta P also increases. Which circuit will have the higher pressure? There are 2 circuits. What are they? All right, which one will have a higher pressure? The systemic, right? Because the systemic is the much longer circuit, right? Because it's got to go all over your body. But the pulmonary circuit just has to go like, I don't know, a couple inches or whatever over to your lungs, because everything's right here, right? Not that far. So the systemic circuit, which is much longer, I'm sorry, don't write that. The pulmonary circuit, which is much shorter, than the systemic. So the pressure there should be less. And indeed, if you measure those pressures, which you do and you can, the pressure in the systemic circuit is about 80 to 120 millimeters of mercury. Let me remind you where this measurement comes from. If I have a manometer and I have a pressure on this side that's pushing down, that would be the pressure that I want to know. It pushes a fluid up on this side. This distance would be that 80 to 120 millimeters. It would be filled with mercury, and this would be my pressure. That I would be required to have a pressure over here that would push that fluid up 80 to 120 millimeters. Whatever the height is, that would give us the pressure. That's where that comes from. The pulmonary circuit, on the other hand, has a much smaller. It's like 10 to 25 millimeters. So a lot smaller, factor of 10, almost. HG, y'all know what that stands for? It's not the TV channel. Mercury, right. And why do we use mercury in a pressure measuring device? Is it because it's toxic? It is toxic, in fact. It's because it's silver. This is pretty. Why do we use it? It is a liquid, and that's important. But I mean, we could use water or wine, like from. Well, the density of water is also constant. But why do we use mercury? Now remember, sort of the viscosity is sort of related to that. How is mercury different from water? Because you could put water, and water is cheaper, it's less toxic, it's easier to find. But how big would your manometer be if you were using water? It would be huge, right? So we use mercury because it is denser. Yes, it's a lot more dense. So that's a good question for the test. We talked about it in the first section. We use mercury in a manometer or barometer because it's so dense. Remember we talked about barometers and how if we used water, the first guy that built the barometer, Bernoullis or whatever, that he had to build a barometer that's like 10 meters tall because he used wine, and that's why we use mercury. Remember that? Yeah? Okay. Blood pressure measurements. Are they gauge or absolute? Remember those two measurements? When I'm measuring blood pressure, is that a gauge measurement or an absolute measurement? It's a gauge measurement. Because remember, absolute pressure is equal to the gauge plus the atmospheric pressure. And so atmospheric pressure is really high. Atmospheric pressure is like 700 millimeters of 760 millimeters of mercury. So these pressures in our blood pressure are gauge measurements, which are quite small. Atmospheric pressure is 760 millimeters of mercury. You don't need to know that number. I gave it to you early on, but you just need to know that it's pretty big, atmospheric pressure. So when I'm doing blood pressure measurements, I'm looking at the gauge pressure. In fact, most pressure measurements, practically all pressure measurements are gauge pressure, that I just assume that the atmospheric pressure everywhere is the same, which it is mostly. So when we're doing blood pressure, when you're measuring blood pressure, we have two different numbers. By the way, this isn't the systemic and the pulmonary circuit. That's two pressures in the circuit, but that's not what you're measuring. But when you are measuring, you measure two numbers. For example, the first would be 120 is a pretty good number. That's the pressure when the heart contracts. Hey, April. We're glad to see you. So it's the pressure when the heart contracts. This is called the systolic pressure. Sure you know that word. This is the pressure when the heart contracts. I guess I just repeated that. Sorry. And systolic actually means contraction. So if you forget the answer, just think back to your Latin or Greek or whatever root that is. Systolic means contraction, and then you'll know the answer. Okay. And then the bottom number, the 80, is the pressure when the heart relaxes. This is called the diastolic pressure. And it's the pressure when the heart relaxes. And diastolic means a drawing apart. Okay. We have two applications in the heart. One is Boyle's law, and then the other is Pascal's principle. Really, the most appropriate application is Pascal's principle. Let's talk about that first. Pascal's principle, what do we use to describe with Pascal's principle? It has something to do with pressure being constant from the system. I was going to put one of these in our house. I'll have to cut my hair. Hydraulic system, right? So Pascal's principle says that if I apply a pressure to an incompressible fluid, that pressure is felt all the way throughout. And we feel those on hydraulic systems, right? So remember our hydraulic systems? I drew one like this. It's like a car lift. I like doing the car lift. My dad used to work at a car shop. Did I ever tell you that? I told you that? Yes. Yeah. I used to work there as a kid, and it was fun. You ever worked in a tire shop? You worked in a tire shop? No way. As a kid, you worked there? Did you crawl through the tires, the big long line of tires, as a kid? Yeah, it's fun. Because, you know, there's a hole that's about this big, and kids can fit in that hole pretty well. My parents had, like, the best jobs when I was a kid. My dad worked at a tire shop, and he let me work there in the summers. And then my mom, she cleaned houses. And so I'd get to go, like, to all the rich people's houses and watch their cable TV, and some of them had swimming pools, and some of them had those switches that you could dim off and on. And one family even had like stairs, so I could scoot down their stairs. They're the best jobs. They used to clean banks too, like in the evening they had a second job to clean banks. And we would go to the bank, my brothers and I, and just like play in the bank while nobody was there. And I remember I'm sorry, this is not on the test, but I remember that in one of the banks, the president, I guess it's the president, had one of those shoe shiners with the rotating things with the red and the black. You ever seen one of those? I'm sure they make those anymore. But there's a little device that's on the floor. You have a little button that spins these soft things that are supposed to polish your shoes. And I go in there with my dirty old sneakers and put them on and polish them up. Oh, those were the days. Anyway, so applying a small force here gets us a big force here. Remember, this is where the car sits. And it's because the pressure at one point is equal to the pressure at another point. And so since I have a small area here and a big area here, I'll have a small force here and a big force here. So when I take the quotient of those two, they'll still be the same. I'm dividing two small numbers, dividing two big numbers. They still give me the same pressure, P. So Pascal's principle is applied in the heart because the heart applies a pressure when it contracts. That increases the pressure throughout the body. Heart contracts. You have this big pressure inside of the heart. And then because blood is incompressible, because it's a liquid, it is incompressible, that pressure is felt all the way throughout the systemic circuit, throughout the systemic and the pulmonary circuit. So that's the application of Pascal's principle. There's also an application of Boyle's law. I'll do it in blue. Boyle's law is really only supposed to be applied to gases, but we can think of it as being applied to the heart as well. Boyle's law, if you remember, B is for breathing. Remember the inhale, exhale? Boyle's law describes the relationship between what and what? Volume and pressure. So Boyle's law says that PV is equal to a constant. And if I make my chest cavity really big, V goes up, the pressure goes down. And that's why I inhale when I make my chest cavity big. And the same is true for the heart, that if I make the volume of my heart small, the volume of the heart gets small in what? Contraction or relaxation? Relaxing or drawing apart. It gets small when you contract, right? So that's why you get a big pressure. So if the volume goes down, that means the pressure goes up. But Boyle's law is really just supposed to be for gases, but you can sort of think of it for the heart too. All right. Let's try these. First one on the top, which of these is greater? The systolic, the diastolic, are both the same? All right, let's stop at 40. Stop at 40. Oh, good. We got a joke. It's not a very good joke, but we'll tell it anyway. How do you count cows with a calculator? Okay, systolic, that's a contraction, right? Systolic means contraction, so that's where you have the highest pressure. I could also ask you a similar question like, where is the pressure greatest in the pulmonary or systemic? Or, excuse me, where is the pressure greatest? Well, I could ask a number of questions. Where is the pressure greatest? In the pulmonary, or the pulmonary artery, or the aorta? What would you say? The aorta, right, because it's going into the systemic circuit, which it needs a higher pressure to go through the systemic circuit. I could ask you, where is it higher? I think you've already asked this. The aorta or the vena cava? The aorta too, right, because that's the beginning of its circuit, and so it has a higher pressure there. So be prepared for those. Let's try this one. According to the flow equation, what happens to the speed as area decreases? Okay, doing pretty well. I'm going to stop at 30. Okay, A is right. The flow equation, Q1 equals Q2. It just says that the flow rate is constant, so A times V is equal to a constant value. That means that as area decreases, the speed increases, so A is right. All right, let's try this bottom one left. Which of these causes the distinct sound when measuring the diastolic pressure? Many of you have it right. 12 of you have it right. Feel free to share your answer. Talk to your neighbor. Talk to your neighbor over there. Yep. Okay, let's stop at 43. 43. Okay, B is right here. The turbulence is, let me look at something. So if you remember laminar flow, why don't you put D? Laminar flow is where I have these fluids that are all flowing in a straight line, and they're not interacting with one another. But when I have the heart and that diastolic pressure, when it's drawing apart, it's like it's sucking in more blood to come into the heart, and then it compresses down again. You like my sound effect? That's what it sounds like. That's not really what it sounds like. So when it's drawing apart, it's like it sucks in all that blood. Is it a laminar flow then? No, it's crazy up in there. Like you got stuff coming in, it's all mixing up, getting all frothy. So that is a turbulent phenomena, and that's what caused that distinct sound. All right, so for an IV, where should you insert the needle? In the vein or the artery? In a second, we'll ask why. But now, if you want to put in an IV, where are you going to put it? In the vein or the artery? Okay, looks like most of you know the answer. Do you know why? I'll see you in a second. So I'll stop at 25. 25. Okay, good. A is right. You want to put it into the vein. Do y'all know why? Why? The pressure, right. So the vein just has a lower pressure, and so it's easier for stuff to go in. So vein is low pressure. Right, because it's at the end of the systemic circuit, so that pressure is just decreased. I don't usually swear, but this joke is worth it. Y'all ready? If you're offended, just sort of cover your ears. What did the blanket say when it fell off of the bed? Oh, shit. Okay, so what happens to the speed of the blood as it moves from the aorta to the capillaries? Does it increase, decrease, or stay the same? We've already had this. Yeah, it stays the same. Oh, wait. No, I'm sorry. The flow rate stays the same. Let's write that down. So Q is constant. But the speed of the blood when it moves through the capillaries, is that faster or slower than it is in the aorta? What do y'all think? So yeah, let's think of that. So imagine if I go to a smaller pipe, I would have a relatively small speed here, but then you're right, I'd have a big speed there. So you might think with the capillaries that you'd have a bigger speed, right? The fact is, in the capillaries, it's really, really slow. The blood is going through the capillaries very slowly. So the speed of the blood as it moves from the aorta to the capillaries is going to decrease. Well, that doesn't make any sense because, like we just said that the equation of continuity would say that the speed should increase as you move from a bigger thing like the aorta, stick my pinky into the aorta, into a tiny little thing, which is just, I don't know, microns across. So what's up with that? Why does the speed decrease when it goes into the capillary? Is it a closed system? Yeah, it's a closed system. Huh? It's the same blood, right? The viscosity is still the same.
It's because of how many capillaries you have?
Right, because of how many capillaries you have. And so what is the net cross-sectional area of the capillaries? Is it bigger or smaller than the aorta? It's a lot bigger. So the capillaries, if you add them all up, have an area that's bigger than the aorta. Let me write that down. So the total area of the capillaries is bigger than the aorta. Just because you have a lot of capillaries. But the flow rate's still the same. The equation of continuity still applies. And in fact, going from the artery to the capillaries really looks more like this, where this would represent the aorta, and combined, this would represent the capillaries. But they don't get smaller, they get bigger when you take them all into account. Okay, as blood flows, the pressure differential drops. Okay, we sort of talked about this. Let's try this question. This is the question right here. Y'all can read the preamble right here. Or actually, no, let's do, these are two questions. This is A, B, or C. Let's do that one first. What happens to the flow rate? I don't know. Never mind. No. Yeah. No, let's answer it. We're good. Go ahead. Go for it. What is the answer? Don't like this question. I'm sorry. I'm just going to exit out, okay? And you do the same. Okay? And just forget about your answers. I'll just get credit for them. Everybody get credit for them. All right. We're getting close to the end of the class period, so let's just make some decisions about the exam. We're close to the end of Chapter 2. So what I'm inclined to do, what am I inclined to do? I'll let y'all decide. So I could make a video. It wouldn't be really long. I would just finish up the rest of these. It'd be about 15 minutes. And then we could include things about the eye and the brain and the bones on the exam. Or we could just stop and say, well, we're going to skip the intravenous. We'll do the next couple little things, and we'll just stop wherever we stop, and that'll be the end of the exam. But then you won't be tested ever on the eye or the lungs or the brain or the bladder. But the thing is, I think that those are the easier portions of the chapter because you've had a lot of that.
Yeah.
All right, so I could give you a 10 or 15 minute video, a screencast, and you watch it. You can fill in the rest of the notes. Or we can just stop. I'll let y'all decide by clicker. So you can vote in, you can click in, and there are going to be three options. A will be create a video, and it'd be on the test, right? B, just stop wherever we stop in about 10 minutes.
No matter what, it's 50 questions, right?
Huh?
No matter what, it's 50 questions, right?
Yeah, it'll be 50 questions still. No, I don't like to push exams back because many of you probably plan ahead. I don't like moving exams. I'm sorry. I give you that schedule ahead of time for that reason. And then C is just I don't care. So click in and tell me what you want to do. I won't show the options, but I'll report the decision.
So we don't do the lab and the eye step is going to have more questions from the other steps to make it 50.
Yeah.
Oh, so it makes it, you might as well get the easy stuff and get to easy points.
All right, y'all just click in. It'll just be a majority, whatever has the most answers. All right? Okay, let's stop. Almost all of you want a video. Great, thanks. I'm going to stop, okay? Yeah, all but about 5 of you wanted the video, so we'll just do the video. So I'll create a video. We're not leaving yet. I'm gonna move ahead just a little bit, but I'll create a video that will cover the last 2 systems, and they will be complicated questions. They'll just sort of be recall of the information about, you know, the parts of the eye, the parts of the bladder, those sorts of things. I'll try to make it clear on the video what to expect on the test. Don't worry about the IV. You can skip IVs in your book. So if you're following along in the book, there is a section on intravenous medication, but you can skip it completely. We'll pick back up on the coronary arteries. Coronary arteries, the artery can be blocked with cholesterol. And changing the radius of the artery affects the blood flow. Q is going to be constant because it's a closed system. But according to the Poisson equation, pi r to the 4th delta P over 8 beta L, that we talked about this actually, that if I change the radius, if I decrease this, then the systemic pressure, the change in pressure between the aorta and the vena cava is going to go up. And it can go up by a lot. So if R is halved, for example, I will multiply my change in pressure by 16, for example, because half squared is 16, or it's 1/16. Okay? 2 times 2 times 2 times 2 is 16. Let's try this one on the left. All right, let's stop at 35, 35. Okay, good. A is right. It's going to increase, and we're going to skip this question too. And arterial collapse, we already talked about it, that if I have an artery that is blocked partially, like that, as the velocity increases here, according to the continuity equation, the localized pressure will decrease. Notice how I wrote this differently, that I didn't write delta P. Delta P is the difference in pressure between 2 spots. This is just the localized pressure at that point. And if that occurs, the artery can collapse. That's generally bad news if that happens. Okay, I'll pick up on the video with lungs, the eye, the brain, and bones. Okay? I'll try to get that video done maybe today, but no later than tomorrow. So I'll send it out to you on YouTube so you can catch up with that. But in the meantime, be looking over the other chapters, 0, 1, 2. Okay? When a good showing on this exam, I want everybody with A or B. Right? We can do that? It's possible, and absolutely is possible. If you have to prep for it, it's going to take some work to get ready. Don't do that. See ya.